Imagine a busy playground where many children want to play on the same swing at the same time. If they all jump on without waiting, the swing could break or someone could get hurt. Concurrency control is like the playground rule keeper who makes sure each child gets a turn in a safe order. In a database, many transactions the children try to read or change the same pieces of data the swing. Without a rule keeper, they could interfere with each other, producing wrong answers, lost updates, or corrupted data. So concurrency control is necessary to keep the database consistent, just like the rule keeper keeps the playground safe and orderly. Two-phase locking 2PL is a simple set of rules that tells each transaction when it can ask for a lock and when it can release it. Think of a transaction as a person who first gathers all the toys needed for a game, the growing phase, and only after the game is over puts all the toys back, the shrinking phase. In 2PL, a transaction may request new locks only while it is in the growing phase. Once it releases its first lock, it enters the shrinking phase and cannot ask for any more locks. This two-step behavior guarantees that the order in which locks are taken is consistent, preventing the kind of chaos that would happen if people kept picking up and putting down toys at random. Locks come in two flavors, just like a library has two ways to let people use a book. A shared lock, also called S-lock, is like a reading room where many people can look at the same book at the same time. They only read, they do not change the words. An exclusive lock, also called X-lock, is like taking the whole book home to rewrite it. While you have the book, no one else may even read it. In a database, a transaction that only needs to read data asks for a shared lock, while a transaction that wants to change data asks for an exclusive lock. Shared locks can coexist with other shared locks, but an exclusive lock is alone. It blocks both shared and other exclusive locks. Strict 2PL is a stricter version of the basic rule. It says never release any lock until the transaction has completely finished. This is like a child who, after borrowing a toy, keeps it until the game ends, even if they are done playing with that particular toy. Rigorous 2PL goes one step further. It requires that both shared and exclusive locks are held until the end. This makes it easier for the system to roll back a transaction because all the data it touched stays locked until we know whether the transaction succeeded or failed. Both variants keep the database safe from dirty reads. A deadlock is like two kids each holding one piece of a puzzle and waiting for the other piece to be handed over. Nobody can finish. In 2PL, deadlocks happen when transactions wait forever for locks held by each other. Detection works by building a wait for graph. Each node is a transaction, and an arrow from T1 to T2 means T1 is waiting for a lock that T2 holds. If the graph contains a cycle, a deadlock exists. Resolution usually picks one transaction in the cycle, called the victim, and aborts it, freeing its lock so the others can continue. The aborted transaction can be restarted later, just like the kid who puts down his puzzle piece and starts a new puzzle, letting the others finish theirs. Explanation: 2PL guarantees serializability, which means the final result is the same as if the transactions had run one after another in some order. To see why, imagine each transaction's lock operations as points on a timeline. Because a transaction never acquires a new lock after it starts releasing locks, the lock intervals of different transactions cannot interleave in a way that creates a cycle of dependencies. Formally, let T1, T2, and so on, Tn be transactions and pi a schedule, a sequence of operations. Define a precedence graph G equals V, E, where V equals the set of Ti, and there is an edge from Ti to Tj if Ti writes a data item X and Tj later reads or writes X, and Ti's lock on X is released before Tj acquires its lock. In 2PL, such an edge can only go from a transaction that finishes its growing phase to one that is still growing, so G cannot contain a cycle. Since a schedule is conflict serializable if, and only if its precedence graph is acyclic, 2PL always produces a conflict serializable schedule. This sketch shows the mathematical core of the guarantee. Holding locks costs time, just like a child who keeps a toy in his hands cannot play with anything else. The more locks a transaction takes, the longer other transactions have to wait, which reduces throughput. That is how many transactions finish per second. However, using larger locks, for example locking an entire table instead of a single row, makes deadlock detection easier, but can hurt concurrency because many transactions are blocked even if they touch different rows. The trade-off is between safety, strong isolation, fewer anomalies, and performance, more parallelism, higher throughput. Modern database management systems tune this balance by choosing lock granularities, using lock escalation policies, and sometimes mixing two-phase locking with optimistic techniques for workloads that read a lot more than they write. In a real system, the lock manager keeps a lock table, a list where each entry tells which data item or page or table is locked, what kind of lock it is, and which transactions own it. The table can be organized as a hash map for fast lookup. Granularity decides the size of the item. Row-level locks give the most parallelism but need many entries. Page-level locks reduce table size but may block unrelated rows. Table-level locks are cheapest to manage but block everything. The lock manager works together with the transaction manager, which tells a transaction when to start, commit, or abort, and receives callbacks when a lock is granted or released. Integration is often done via an API. A transaction calls lock item mode. The lock manager either grants it immediately or puts the transaction in a waiting queue, and notifies the transaction manager when the wait for graph shows a deadlock. This architecture lets the DBMS keep the rules of two-phase locking enforced automatically behind the scenes, while application developers simply write begin ... commit without worrying about the underlying locks.